Welcome back. In the last class, we understood lots about the Fourier transformation, theorems of Fourier transformation, what is a Fourier transformation, what is a band limited function, and what are the theorems like shift theorem, linearity theorem, additive theorem, Nyquist theorem, sampling theorem. All are very important theorems in Fourier transformation we understood in the last class. And also I just worked out especially for the Gaussian function and showed that Fourier transformation of a Gaussian is a Gaussian. But I did not work out other functions. Of course, this rectangular function we worked out in the beginning itself and showed it as a sinc function. Explicitly to introduce Fourier transformation, we worked it out. Anyway, without working out other functions I mentioned to you, the Fourier transformation of Gaussian is a Gaussian. Fourier transformation of rectangular function is a sinc function. And Fourier transformation of delta function is a DC. And Fourier transformation of exponential is a Lorentzian. These are the things which most of these things we use in NMR spectroscopy when we collect the time domain data. Okay. So now, where do you use this in NMR? Where do you come across this thing to understand Fourier transformation so much? First of all, remember when we discussed NMR in the beginning itself, I said we apply a radio frequency pulse and collect the signal in time domain. It is a decaying exponential. Okay. And then when it is an exponential and for time domain function we do the Fourier transformation to get the spectrum. Since it is an exponential function, when you do the Fourier transformation you are going to get a Lorentzian. That is why NMR spectrum is a Lorentzian spectrum. And when you do the Fourier transformation you get real and imaginary parts. And we call it as real part as absorptive Lorentzian and imaginary part is called dispersive Lorentzian. And this is a general expression we use for Fourier transformation. Remember, Fourier transformation of, if you want to get the time domain, this is what is the function you have to use, S of 0 exponential e to the power 5 omega t into exponential e to the power minus t by t2. The time constant t2 is very, very short, then the signal decays more rapidly. If it becomes sharper and it becomes shorter and shorter, then this becomes larger and larger in the numerator. The exponential becomes quite big. As a consequence, it decays very fast. Just this is what you should understand. In the NMR spectrum, what is going to happen? If the signal is decaying very, very slowly like this, that means your spectrum is very, very sharp. It is a Lorentzian like this with width is very, very small. On the other hand, if the T2 is larger here, which is in the denominator of this exponential, then what will happen? This becomes larger value, so signal decays very fast like this. A similar expression we are going to discuss for T2 and T1 as we go ahead for relaxation studies. You will see that the T1 and T2 which comes in the denominator, you can see that here also, there also you will find out that when the signal decays very fast in the xy plane, you are going to get a broad signal. So this is where you understand where the Lorentzian and Gaussian will come into the picture. For example, this is the sine function if I take, sine or the cosine function. The Fourier transformation of this single sine or a single cosine function, only one, it transforms into a delta function with a oscillation frequency. Okay. The Fourier transformation of this, whether a sine or cosine you take it, it will give us to a single frequency. I have taken single sine because it is only single frequency. Single sine if I take, from here to here is the frequency, only one frequency. Similarly cosine, here to here is the single frequency, you can measure it. So then it gives us to a single line. Okay. Whereas if I take the exponentially decaying function, then it transforms into a Lorentzian function like this. I take this exponential decay. This is the FID of the NMR spectrum. You do the Fourier transformation, this is what you are going to get. And this is called real part, this is called the imaginary part. Real part is absorptive like this and imaginary part is like dispersive like this. So this is an absorptive part, is nothing but the real part of the Fourier transformation. This is the imaginary part, is dispersive component of the Fourier transformation. And of course, rectangular function we discussed, it comes as a sinc function sin c by c, sin c by c function. You will come across this in some of the this thing when you are trying to do the NMR experiment. Let us say I am going to collect the signal very fast like this. It is an exponentially decaying function. Somehow the gain of my receiver is huge. I use lot of gain for the receiver. The initial portion of the FID gets amplified like this. Then the FID won't be smooth decaying FID, it will be like this. Then what does it mean? This portion behaves more like a square pulse or a rectangular pulse. If you do the Fourier transformation of such type of free induction decay, you are going to get in each spectrum, each frequency, especially when you have a stronger frequency, strong signal present in your spectrum. Near the strong signal, you get wiggles like this on either side of them. These wiggles are nothing but the sinc function. Please remember, in the Fourier transformation, when you do the NMR spectrum, collect the free induction decay and do the Fourier transformation, if the FID is cut in the initial portion, you are going to get the wiggles like this. They are because of sinc function. You will understand. See, all these things, when you understand Fourier transformation, you go back to do the NMR spectrum and you see all this problem, you can immediately reason out why it is happening. That's why the understanding of this Fourier transformation was very, very important for you. The conventional 90-degree pulse which you use in NMR is a rectangular pulse like this. So obviously, we are going to, when you use the rectangular pulse, the output has to be a sinc function. That is the reason why we use this type of pulse. And a Gaussian function in the time domain, of course, I already showed you, it transforms itself into Gaussian. Of course, this is what is a Combs function, we call it, at different intervals it is repeating itself, and Fourier transformation of it into a Combs function like this, with a period is equal to 1 over t. Okay, this I do not want to explain. Now I will take the time domain signal, do the Fourier transformation of this signal, which gives us the frequency spectrum. Now this is the cosine part. This cosine part is an absorption. Look at this. The center of this is the frequency. Okay, omega. And the dispersion you can see has a phase shifted by 90 degree. The absorptive and dispersive component has a phase shift by 90 degree. That means this is a cosine part and this is a sine part of the Fourier transform signal. When you do the Fourier transformation, you get real and imaginary part. One is a cosine part which corresponds to real part, which gives us the absorption signal, and the sine part is an imaginary part which gives us to dispersive signal. So this is what we are going to get. This is the dispersive signal. Now we use this Fourier transformation, as I told you, very often in the NMR spectroscopy. Like I collect the signal in the time domain, do the Fourier transformation like this, and I am going to get, this is the time domain signal collected. I do the Fourier transformation and get the frequency. I can go back, I have the frequency spectrum, do the inverse Fourier transformation of it, then I will get back time domain signal. I can interchange between these two. Okay. This is normally collected. We collect the signal as a function of time. This is the equation f of omega is equal to integral of minus t to plus minus infinity to plus infinity f of t e to the power of minus I omega t dt. This is a famous important equation for Fourier transformation of time domain in NMR. Remember that. Of course, inverse of that, where you remove the negative part here, it is e to the power plus I omega t dt. If you take it, then you can do the Fourier transformation of this frequency domain. You go back to time domain signal here. Okay. And in the time domain signal, that is free induction decay, we call it, as I explained in the earlier class, in the very first class. Time domain signal is called FID. The signal intensity varies with time. Similarly, in the Fourier transform spectrum, intensity of the peak also varies with the time. Very easy to understand this. Let us say I have two frequencies present in your NMR spectrum. One intensity is very large, huge free induction decay is there. Signal intensity is very large. Other is very weak intensity like this. Both are present. Do the Fourier transformation of it. We will have frequency, one is bigger intensity, other is smaller intensity. The frequencies are different and the intensities of time domain varies. Correspondingly, intensities will be also different in the frequency domain spectrum. This is what you come across. In the NMR spectrum, all are not of equal intensity. Different peaks have different intensities. As a consequence, you do the Fourier transformation, the frequency spectrum also will have different intensities. So it's like the time domain FID has a different intensities, different amplitudes when you are collecting the signal. Similarly, here also the frequency will be different in the Fourier transform spectrum. So of course, folding and aliasing, why it comes, how we can, already we discussed the theorem of folding or aliasing using Nyquist theorem. But if I want to avoid this, what I should do is, the free induction decay which we are going to acquire, I have to digitize at least twice in a cycle. This is a cycle, let us say, at least twice I have to do here, once here or here. If I do once here and once here, then the frequency is not completely specified. This is what we discussed about the Nyquist theorem. So that Nyquist theorem comes here in NMR. If you don't digitize it properly, you are going to get the folded frequency. Okay, that is what I told you in the Nyquist theorem. F plus delta appears as F minus delta. That is what is going to happen here. So to avoid that, what you have to do, the digital resolution you have to maintain in such a way, you have to take twice the spectral width or divided by the acquisition time, that is your digital resolution. You have to manipulate these two parameters in such a way, your digital resolution is such that you have to digitize the signal at least twice in one cycle. Then the frequency is completely specified. Okay. So to characterize the frequency correctly, you have to digitize at least twice. Okay. And this is what it is, Nyquist theorem. So highest frequency in the spectrum you find out. Take the highest frequency of that is what is called a band limit. I told you 1 over SC. It should be digitized at least twice of that highest frequency. I will take the spectral width from, let us say, 0 to 1000 I will take, and my highest frequency is about 900. At least 1 over twice of that you have to digitize it, at least twice of that. That is very important. The highest frequency you have to take it, represent it correctly by digitizing at least twice of this frequency. So this now come to Nyquist theorem. If you don't digitize it properly, what happens? I told you F plus delta appears as F minus delta in the frequency domain spectrum. You get different confused spectrum. You will get yourself confused with real spectrum with the folded peaks also. This is called folding or aliasing in NMR. Remember how the Nyquist theorem comes useful in your NMR spectrum. You have to digitize it properly, at least 1 or twice the highest frequency. That is very important. The magnetization M0 is brought to transverse plane and it decays into XY components. You will have a X component here and Y component here. The detected components of the magnetization correspond to cosine and sine. Because Fourier transformation, when we express it in the complex form, we have cosine component and sine component, both are present. So when you take a time domain signal like this, do the Fourier transformation, you will get, if I call the M0 as the magnetization in the Fourier NMR, I can resolve this into two components, Mx and My. Mx is the X component, My is the Y component. X and Y are opposite, phase shifted by 90 degree. If I have my receiver here, I get a real component here. Then this is phase shifted by 90 degree. This signal will be dispersive signal. So I am going to get the absorptive peak here and dispersive peak here. So this is what I was trying to tell you. You come across this absorption and absorptive component, dispersive component, all those things very often. We will discuss that. So this Mx component is nothing but the cosine omega t and My is the sine omega t. So signal detected in the time domain is proportional to these two constants. The total signal, it comes because of some of these things. See, for example, if I have a total signal, it is a sum of Sf of t, Sy of t, that is X and Y component, that is sum of cosine component, sine component. That is why we can write this form as S of exponential I omega t, sum of these two. Okay. Now what happens if there are many frequencies present in the spectrum? Let us say I have 3 frequencies, omega 1, omega 2, omega 3. Now what I am going to do is individually you can do the Fourier transformation, they are all added up. That is what I told you in the linear theorem, linearity theorem. There are 3 different functions. The FID is the contribution from each of them, they are overlapped. One FID is like this, other FID is like this, other FID is like this, they are all overlapped. And you do the Fourier transformation, individually they are Fourier transformed. That is why you are going to get 3 different frequencies. So if there are many frequencies present in the spectrum, in the time domain there are many free induction decays overlapped. It is an interferogram. And do the Fourier transformation, you are going to get that many number of frequencies present. I took the example here, there are 3 frequencies. The time domain you have 3 free induction decays and frequency domain after doing the Fourier transformation, you are going to get 3 frequencies. Okay. Of course, this is what I said, Ft is a linear process, and because of this, sum of the Fourier transform of this function is sum of the frequencies you see in the frequency domain also. If you have n frequencies, we have n decaying signal in the time domain. I have, let us say, in the NMR spectrum there are 10 peaks. Each peak is different. 10 different frequencies are present. That means in the time domain signal there are 10 FIDs. They are overlapped. Each frequency corresponds to one decaying signal. And Fourier transformation gives n individual frequencies. This is what is the linearity theorem I explained to you. You understood. In the Fourier transformation, so many theorems I discussed. All these theorems in your routine daily analysis of the NMR spectrum while recording the spectrum, you will come across these things. Only thing is you should know what are these things so that you know how to interpret these things at right time. Okay. Now there is a phase correction. Remember I told you, if there is a delay in the acquisition of the signal, what is going to happen? I said amplitude or frequency will not change, but there is a change in the phase. I told you in one of the theorems of the Fourier transformation, when I was trying to explain, I told you if there is a delay in the collecting the signal, then what will happen? Frequency will not change, only thing is phase will change. That does happen in NMR spectrum. You send a radio frequency pulse here. Immediately after this you should start collecting the signal. But what happens is there will be generally some delay will be given, microsecond or something. During that delay, instead of collecting signal from this point, in principle you have to start collecting from this point, or sometimes this point itself, no problem. But then if there is a delay, you start collecting from this point, then what will happen? This is not exactly you are starting at 0, there is a phase error. Phase errors will invariably be present. You need to correct this in the frequency domain. Okay. So how do you correct this? See, appearance of the spectrum depends upon where do you correct the signal. It is at the point time t equal to 0 you have to collect immediately after the pulse. The starting point is not exactly at t equal to 0, you have a phase error called phi. Okay. So now I can incorporate this phase error like this. This was the exponential I omega t, it is power exponential t minus t by t2 I wrote earlier. It is a time domain signal. This is decaying because of this. But now there is a phase error which also I can incorporate like this, exponential I phi multiplied by this function. So a phase term gets introduced into the signal now because there is a delay in the acquisition of the signal. So what happens if there is a delay more? For example, if I have a receiver here, I will discuss about this receiver phase and pulse phase in 1 or 2 classes later. We will come back and discuss. If I have a signal here, I have a receiver is here, signal is here. See, you are going to get a real part here like this. But the signal if here is out of phase by 90 degree, it is imaginary part. If on the other hand, my receiver is here, signal is somewhere here, what will happen? It has components of both x and y, cosine part and sine part present. So it is a mixed phase. Real part is not pure absorptive and imaginary part is not pure dispersive. Both are mixed up. It can happen. But then it is a clumsy spectrum. You need to do the Fourier you need to do the phase correction. What do you do for that? You have to make sure the phase difference between the real and imaginary part is exactly 90 degree. That is what is called the phase correction. If you try to do that, then you can make this like this. Sorry. Other one like this or like this. Okay. So phase correction if you want to do, you have to make the real and imaginary part exactly out of phase by 90 degree. Okay. How do you do the correction to the phase? You can do it in the time domain or also in the frequency domain. In the time domain what you will do is take this frequency, this is a correction factor, exponential I phi, I call it as a correction factor. This is a phase error. A phase error I call it exponential I phi. Correction I put it like this and then multiply these two functions. These two functions can be multiplied. Okay. Now exponential have the property exponential a into exponential b equal to exponential a plus b. Now I am going to do this. If I take this function multiply by the exponential correction factor, then I can call it as exponential correction factor plus the phi error into this function. Now logically you can understand, if the correction factor is exactly opposite of this phase error, you will remove the error. There won't be phase error at all. So you have to make sure the correction of this phase error is opposite of this phase, and then you do that. Set this phi correction equal to minus of phi. This exponential of 0 here becomes 1, here this becomes 1, then what you are going to get is exponential of correction factor of signal in the time domain is without any phase error. There is no phase function involved now, because with the correction factor I added to the time domain, I have removed this phase error. So this gives a spectrum without any phase error, and the real part corresponds to the pure absorption and the imaginary part corresponds to the pure dispersive signal. If you apply correction to the phase, that means you have to ensure that the signal is collected immediately after the pulse at time t equal to 0, so that phase error will not creep in. But it so happens it will not be perfect, there will be always some inherent phase errors, but then you can apply the phase correction like this, and then you will get a signal which is free from phase errors, and the real part corresponds to pure absorptive spectrum, and the imaginary part corresponds to pure dispersive signal. So similar to FID, we can also do the correction in the spectrum also, same way. Like I multiply the free induction decay by this exponential function, the time domain signal. Then I did the Fourier transformation and I ensured that there is a phase error is removed. Do the same thing in frequency domain, it is possible. I multiply this phase error correction factor to the frequency domain function, that is also possible. This one, there are two types of phase errors. One is called the frequency dependent phase error, other is the frequency independent phase error. This is called frequency independent phase error if you can do it in frequency domain. Okay. Other one is first order correction, it is a frequency dependent phase correction. So this can be done manually or automatically. And another thing what is going to happen is, we always use some window functions. What are these window functions? Of course, if you have attended my first course, you would know how we manipulate the time domain signal to get this frequency domain spectrum with a larger line width, smaller line width, better resolution, better signal to noise ratio, all those things. For example, I have a time domain signal like this. It is decaying, okay, no problem, I have signal all through. If I have collected the signal for a length of time like this, for this much time, and then signal decays like this very fast, rest of the thing is only noise. What is the point in keeping the noise? You will add only noise to the spectrum. What I will do is I will multiply this by another decaying exponential like this, and then it will cut off when there is a decaying exponential. So this portion will become 0. Okay. When that portion becomes 0, what are you going to have? What you are going to get? You will see when you multiply by that, you are going to get less noise, because you are removing the noise by multiplying by an exponentially decaying signal. So this portion you cut it off, so reduce noise. But what did you do? You multiply by another exponential function which inherently adds up. There is additive theorem, I told you, no, these two will add up, and because of that the line width becomes larger. For example, the width of the spectrum, let us say, is 1 Hertz. You multiply this function this by an exponentially decaying function at 2 Hertz. Then what happens? It will add up, the line width will become 1 plus 2, 3 Hertz. So you can play with the window functions, either to reduce the line width or to increase the line width or to reduce the noise, like that. These are all several wave functions which you multiply, which you can do after you are acquiring the data in the time domain. After acquiring the data and multiply with these window functions, and see that the type of frequency domain spectrum what you get could be highly resolved or less noise and everything. And many window functions are there. One of them is the exponential function, Gaussian function, trapezoidal function, sine wave function, shifted sine wave, varieties of window functions are possible. Depending upon the type of free induction decay you are going to get, how the time domain signal you are seeing, you can use one of these things function to get a right spectrum of your choice. For example, look at this signal. It is a time domain decaying signal. This is multiplied by an exponential function LB. We could filter out the noise, now I told you, by multiplying by this. If there is a lot of noise in this later portion of the free induction decay, that all get removed. Okay. So multiplication of time domain by an exponential is what? Is nothing but a convolution in the frequency domain. I told you convolution of two functions in one domain is multiplication in the other domain. In the time domain now I am multiplying two functions. One is an exponentially decaying function. For that I am multiplying by another exponentially decaying function. I am multiplying by two functions. That means I am convoluting these two functions in the frequency domain. Now we found the use of convolution theorem in NMR which we discussed. This is the convolution theorem. So we multiply by this time domain signal and ensure that later part of the free induction decay, the noise is cut off and we are going to get the better signal to noise ratio at the expense of the line width. That you do not forget. Alternately, you may ask me a question, instead of exponentially decaying function, what happens if I multiply exponentially increasing function? Instead of decaying like this, if I increase like this, if I multiply like this, very interesting thing will happen. Then what will happen is noise keeps adding up here. The signal becomes very noisy. But there is a this price for that. See, here you pay the price of line width. In this case there is an advantage. Price you paid was the noise, lot of noise came, but the gain is resolution. You get better signal, better resolution, highly resolved spectrum you are going to get. The line width gets reduced. So this is how you have to play with the window functions of your choice, either to increase the signal or to decrease the signal like that. So this is what multiplication of the time domain exponential correspond to convoluting the frequency domain. Now what happens is, in the frequency domain each peak is convoluted with the same exponential function. That is a very important thing. If there are 10 free induction 10 signals, there are 10 decaying signals in the time domain. If there are 10 frequencies present, and now when you convolute it in the time domain or multiply by an exponential function in the time domain, then each of these is multiplied by that particular exponential function what we give. That means in the frequency domain what is happening is each of these peaks is convoluted by the same exponential function. The line width will be uniformly added up. It is not differential. If there are 10 peaks, you add up, let us say I multiply with the exponential decaying function by 2 hertz, line width is added for 2 for this, 2 for this, 2 for this. Each peak in the spectrum will become broader by the same amount. Okay? This is what is happening in the when you multiply by the decaying exponentially decaying function. When you do this in time domain, these are called window functions in NMR, which you use very often. So with this I think I have touched upon lot of things about the Fourier transformation, where I have discussed right from Fourier series. I brought you to the Fourier transformation to understand Fourier transformation everything. We discuss how to get the Fourier transformation, how a discrete function will become when you can make it continuous here, how it I showed you how we can make it continuous and get all the frequencies present in the time domain. And then we discussed a lot of theorems like convolution theorem, similarity theorem, additive theorem, shift theorem, Nyquist theorem, folding theorem, all those things we discussed. And I showed how they are useful in NMR. Without your knowledge, when you give the sample to an operator, he will put the sample and type some command and give you the spectrum. But all these things are happening in the spectrometer. But if you are doing research in NMR, if you are sitting with the spectrometer, if you want to understand this, what is happening in this spectrum, all these things you have to understand. When you understand these things, you will know how to solve these problems. So this Fourier transformation, the theorems of Fourier transformation especially, you will be coming across very often in the NMR spectrum. So with this discussion, I think I have given you fair amount of information about Fourier transformation, because this being a little advanced course compared to the previous course we discussed, that was more elementary and for the beginners. I just wanted to introduce little mathematics for it. Of course, without mathematics no NMR. But remember, I did not go to many of these steps in detail, because if I had to work out like a chalkboard, chalk talk I can give, but then it will take ages. This much to work out all these things using giving a chalk talk, working out each step would have taken several more hours of my talk. So many of them I skipped, assuming that because they are all basic simple integral functions, simple trigonometrical functions, you will use it very often and you will know that. Of course, while working out one or two, if I have made a mistake of sign or something, you will find out very easily also, because there are simple integral calculus which you would have studied in high school or PUC like that. So, with this I am going to stop. Next I will go to a different topic, that is, and let me see whether I can introduce quantum mechanical analysis, the NMR spectrum, or phase cycling. I will see whatever the interesting thing which are possible, I will try to incorporate. I will bring it to you, I will discuss that in the next class. Thank you very much now.